notes that got cut off. So when we do the noble gas configuration, the shortcut, what you can do is go back, and so we're doing the shortcut for iron. The noble gas that comes before iron is argon, and I know since argon's a noble gas, its electron shell, they're completely full up. So instead of writing all this, since this is argon's configuration, I can just write argon in brackets and then continue on with my 4s2 3d6. This can only be noble gases. You can't do this with any other element. So try writing the noble gas configuration, the shortcut for these three elements. Pause it and then come back. So for titanium, where's titanium? Here's titanium. The noble gas that comes before it is argon. And then it was 4s2, I have to look back because I don't have a periodic table with me, 3d1, 2, sorry, 3d2. Same thing for vanadium. Vanadium would be argon, 4s2, 3d3. Chromium is an exception, so we're not going to do chromium. So orbitals fill in an order. They go from lowest energy to highest energy. Adding electrons can change the energy of the orbital. So full orbitals are the absolute best situation, like noble gases. Everybody wants to be like the noble gas. But if you can't be full, then half full is the next best thing. So there are two exceptions. You have to know both of them. Copper is one exception. This is what you would expect. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d9. But it actually is 4s1, 3d10. That makes this D shell full and this half full, which is just more stable. Chromium's the other one. You would think that you get 4s1, you would think that you get 4s2, 3d4, but having two half-full shells is better than this. Okay, so when we do electron configurations for ions, just remember that ions are atoms that have lost or gained. So if you have a positive ion, a cation, it has lost electrons because electrons are negative. And if you have an anion, a negative ion, that means you have gained electrons. So I'm going to write iron, 1s2, 2s2, 2p6, 3s2. I have to go back and look at my periodic table. 3s2, okay, 3d6. Sorry. 3p6, 4s2, 3d6. Okay, this is a neutral atom, but here this is 3+, so that means I've lost 3 electrons. So, whoops, that was a little too big. So this will be 3d3. So you have to be careful because this could be the electron configuration for vanadium, or it could be the electron configuration for the iron atom. The iron ion. So you just have to be careful on multiple choice questions. So do the electron configuration for magnesium. 1s2, 2s2, 2p6. It should be 3s2, but it's lost 2 electrons. So we lose this and we lose all of it. So this could be the electron configuration for magnesium ion or neon. Fluorine, we would expect 1s2, 2s2, 2p6, 2p5. But since it's gained, has a negative charge here, it's gained 1, we add an electron. So this is 2p6. Okay? Sulfur, 1s2, 2s2, 2p6, 3s2. Should be 3p4, but it gained 2 electrons, so 3p6. Okay, valence electrons. These electrons are responsible for the chemical properties of an atom because they're in the outer energy level. They can react with things. Your valence electrons are your S and P electrons in the outermost energy level. So if I have 1s2, 2s2, 2p4, I have a 2 energy level and a 1. So this is my highest energy level. If I have 1s2, 2s2, 2p6, 3s1, 3 is now my highest energy level, so I have 1 valence electron. Electron dot diagrams are a way of keeping track of your valence electrons. So you write your symbol, and then you put your dots around it, 1 for each valence electron, and remember they don't pair up until they have to. That's Hund's rule. So let's do nitrogen. Nitrogen has 5 valence electrons because it's in group 5A, so we write the symbol nitrogen, and then 1, 2, 3, 4, 5. That's it. Okay, there y'all go. I hope that made a little more sense.